And this is part of the last section in the 4.1 assignment. Remember I told you you could do most of it, but there's a few at the end we wouldn't have talked about. Well, this is the few at the end we haven't talked about yet. Whoops, that's back going. Okay, so we're gonna practice some. This is kind of a really quick and easy factoring technique that we use when it fits. Let's take a quick example like from last week. If I did something like, let's say I told you to factor x squared minus x minus 12. What does that equal to in factored form? Minus 4?
Yes. Yeah.
Right? X plus 3 times x minus 4. Okay, and remember we said earlier that if we go from this expression to this expression, that's what we call factoring, if we're breaking something apart into a product of smaller factors. And if we reverse that process and start here and go to here, what do we call that? I mean, it's expanding is the word we use in math. When we multiply stuff out and collect like terms, that process of simplification we call expanding. But really, in essence, what we're doing is multiplying, isn't it? Okay? So what if we did something like this? What if we wanted to start off with something of the form a squared minus b squared? We know what that's going to factor into. We could say it again. That's it. Yeah. Okay. That's it. So, and that's what we call a conjugate pattern, by the way. It's a conjugate pattern. Remember us talking about conjugates? We've talked about them. I think I've thrown that word out a couple times. Conjugates are just when I have two terms, if conjugates are things like a plus b and a minus b, where the terms a and b stay the same, but in one case we're adding them and in the other case we're subtracting them. That relationship, that's called a conjugate relationship. We'll talk a lot more about that as the year progresses. But what we find is that when we factor something that looks like what's called a difference of squares, something squared minus something squared, it's always going to factor into this conjugate product pattern. It's always a plus b times a minus b. So this is the factoring direction. And this is the expanding direction. And we can take advantage of that. We can take advantage of that when we want to factor something like, for example, what if you're supposed to factor? What if we were supposed to factor something like, let's say, x squared minus 100? Okay. Could we write that as a trinomial? We could. If I wrote that as a trinomial, what would the coefficient of x be? There is no x term there, so what must its coefficient be? Be 0, wouldn't it, right? So I could, and I don't want you to do this. I mean, this is not the way to do it, but I just want to show you that this works. If we wrote this out as x squared plus 0x minus 100, we could play we could factor this, right? We could look for magic numbers. What would the numbers have to multiply to?
Negative 100.
They have to multiply to negative 100 and add to. Okay, so what's that tell you? negative 10 and positive 10 in either order, right? If they're adding to 0, they have to be the same, don't they, right?
Yeah.
But we can just recognize that if we can think of this instead of having to go through that whole exercise, if we can just think of this as being a difference of squares, something squared minus something squared, then we can just follow our difference of squares pattern. Well, what are the squares? Obviously, this square is going to be an x, right? 100 is what squared? 10. Okay, so then that acts like my a and that acts like my b, and we're just following that pattern, right? Everybody see that? So we end up with, remember the pattern says a squared minus b squared equals a plus b times a minus b. So what's my a? Well, my a is an x, my b is 10. Here my a is an x, my b is a 10. Easy, right? No big deal. Okay, that's the difference of squares pattern. Okay, so then what about a sum of squares pattern? Let's just try that. So what if we had something like this? What if we had something like a squared plus b squared? What's that going to factor into? Like, for example, let's just try it with numbers and just run a little experiment. Well, like, what if my a was an x? We'll use 10 as our b again. What if I had x squared plus 100? Right? If I wrote that as a trinomial, once again, that's x squared plus 0x plus 100, right? So what would my magic numbers be then that would multiply to 100 and add to 0? Ah, but they don't multiply to positive 100, do they? Hey. Now, if I'm multiplying two numbers together and they're multiplying to a positive, what does that tell you about the signs of the numbers? They have to be the same. Well, how can I possibly add two numbers of the same sign and get 0? I can't. The answer is I can't. Right? It's impossible. So I don't get an answer, and we can see that when we try to expand this and use our magic number approach, right, with the trinomial. So what that's telling us is, and this is important, that a squared plus b squared is already factored. You can't factor it any further than that. In other words, there is no pattern. So when you see something that fits the sum of squares pattern, that's a non-pattern. The answer is you cannot factor those. They're factored as far as they can factor. This is what we would call, for example, right here, this is what we call an irreducible quadratic factor, which that's a word we'll use when we get into factoring polynomials. Meaning you can't break it down into a product of two linear factors. You know, x plus this times x plus this. It doesn't work. It never works. Okay? All right, so let's just try a couple of these then. I'm just going to pull some up from the assignment. Let's see how we do. All right. Oops. Hey, focus. All right, so try this one. Okay, on your notes, we'll talk about this, but just give that one a try for a second. See, think about it for a moment.
So it's
This is from the assignment. It's from I just pulled the random problem off of the 4.1 assignment. But take a second and just think about that. We'll go through it in just a moment. Okay, let's have a look. What's our thinking on this? So click all the Chromebook should be closed all the way. Let me get everyone's focus up here. So what are we going to do with this? What do we always want to try to do if we're factoring something? We always want to see if we can factor out a greatest common factor. It's always going to be a great idea. It's always going to help us. Is there a common factor? There isn't, right? Other than 1. There's no number that divides into 36 and 49. So we're stuck with that. We're stuck with this the way it is. I mean, we could try to go the magic numbers route, but we don't want to do that. That's not efficient. What's the only pattern that this could potentially fit? Okay, the only pattern it could fit is a difference of squares, right? So the only pattern it could fit is the a squared minus b squared pattern. Have you guys done this before?
No.
Okay, I just wanted to know. And what is that pattern again? A minus b times a plus b. Either order, doesn't matter, right? Doesn't make a difference what order you write those in. So now the question is, can we write this? Can we write this as a difference of squares? Because it's not written as a difference of squares now. Everybody see that? It's not written as something squared minus something else squared. Can it be written using that pattern or template?
Yeah.
Okay, well, if so, what would go in there?
6x
6x, right? Everybody agree? The term 36x squared could be written as the quantity 6x squared. What about 49? Okay, so then now all we have to do, that's our A and that's our B, right? So we're just going to follow our pattern. We're going to get A minus B times A plus B. And we're done. It's backward. Okay. So when you're trying to factor something that involves 2 terms instead of 3, it's always going to be easy, right? There's really only a couple things that could be happening. We've done some problems like this already. Remember doing a problem like I gave you some previously like this, like how about, I told you to factor that. It's easy. What's the only thing we can do here? Okay, I could undistribute a 3x, right? If I undistribute a 3x, what's left behind? X and minus 4, right? And we're done. Okay, that's it. So one of the 2 things that could happen if we're starting off with a binomial, we're trying to factor a binomial, one thing is we could factor out a common factor and we're done. There's nothing else I can do. The other thing that could happen is it matches my difference of squares pattern, and so I can use that pattern. Okay, it could be a combination of both. What about something like that? Okay, I can take out a 5x, you're saying, right? Okay, negative 5x is what I want to take out, and that's actually really important. I want to take out a negative 5x. And the reason I want to take out the negative is because that's the sign of the coefficient of the biggest power. We call that the leading coefficient, right? If I write, in next unit, we're going to talk about all these functions as polynomials, where we write powers of x, we have a number times a power of x plus a number times a power of x. All these problems that we've dealt with, they're really just, that's really just a polynomial. But we don't call it that. We call it a quadratic trinomial right now because we're talking about quadratics. But it's just 1 times x squared plus negative 1 times x plus negative 12 times x to the 0, which is just times 1, right? This is times x squared, that's times x to the 1, that's times x to the 0. Now that's future units we're going to talk. We'll talk about polynomials in detail. But when we write polynomials in their standard form, and it's useful just to think about this, we always want to write them from the biggest power down to the smallest power of the variable, right? So when we write this example here, when we write this in standard form, in its simplified form, we want to put the x cubed term before we put the x term, right? So here's our rule. When we're factoring out a greatest common factor, we always inherit the sign of the leading term. Okay, so if the coefficient of the biggest power of x is negative, we're going to factor out a negative. Okay, let me write that down. So you might want to put this in your notes. The GCF always inherits the sign of the leading coefficient. So it becomes negative. Okay? And then what's left over when we divide a negative 5x away from each term? Negative 5 times what is 80? 16, good. And then x times what is x cubed? There you go. 45x divided by negative 5x is, okay, and how could I check this real quick to see if I got it right?
Just
Distribute. Yeah, distribute and see if I got the original expression right. Okay, so far so good. Okay, now what? Okay, so now we're done. The negative 5x is done. That's what we call a monomial. Mono meaning one, right? It's a factor that consists of just a single term. So it's taken care of. But now I've still got this binomial, this purple binomial, that I've got to see if I can factor. Maybe I can, maybe I can't, right? But I need to know. If I can, I have to go further, because when we're asked to factor something, the implication is we're supposed to factor it completely. Okay, so now we're here. So let's go down. Can I write this purple factor as a difference of squares? Okay. Could, couldn't I? The 16x squared I could write as what quantity squared? 4x. And then obviously that's going to be a 3 squared, right? And out front I've got my negative 5x. But this part right here is going to factor by the difference of squares, isn't it? Right? This is going to give me, I'm going to get my negative 5x, and then this purple stuff is going to turn into my a plus b times my a minus b, right? So I'm going to get my 4x plus 3 times 4x minus 3, either order. Everybody see that? Just following that pattern. And now we're done. That's as far as I can break it apart. Okay. Make sense? Okay. What about this guy? Is there a common factor? Yeah, there is. I can take out an x squared, can't I? Okay. So I could take out an x squared. If I undistribute an x squared, I'm left with what? Plus. Okay, now that looks like a sum of squares, doesn't it? Right? I could think of that as the quantity 5x squared plus 6 squared, right? But does that give me anything? No, because remember, there's no factoring pattern for a sum of squares. So we're done. That's as far as we can go. This won't factor because it's got a plus sign between those squares instead of a minus sign. And so that's our answer. Can't go any further. How do I get a comment? Okay? Make sense? Okay, so that's it. So that's the sum and difference of square stuff is not that big a deal. Just using those patterns to quickly factor binomials that fit. Okay, so what about this then? Quick review of the stuff from 4.2. Jim and Cahill, need you guys focus up here, please. So what about this? What does this language mean? It says use factoring in the zero product property to find all real zeros of the quadratic function. So what's it mean to find a zero of a function? Find where it crosses the x-axis, and I do that by setting the function equal to 0, right? In other words, I'm just setting y, which is f of x, equal to 0, in order to solve for where y is 0, which is on the x-axis, right? So that gives us the equation x squared minus 8x plus 12 equals 0. Here we've got a nice little compact quadratic trinomial. A is 1, so if this factors, it's going to be easy. Are there magic numbers that work? What are they? -6 and -2, everybody agree? They have to both be the same sign and they have to both be negative because they multiply to a positive and add to a negative. And the numbers that work are 6 and 2, right? So then what are the zeros? What are the solutions? Good, because we know that we're going to apply the zero product property, right? We know that the product of factors is 0 when the individual factors are 0. So we just ask ourselves, what value of x makes that factor 0? 6. What value of x makes that factor 0? 2. So we get x equals 6 or x equals 2. Okay, those would be my zeros. Okay, how about this one? Looks like a mess. What do I have to do first? Set it equal to 0. So I've got to put it into standard form. I've got to write it as an equation in standard form, which means it's set equal to 0. So if I'm going to push everything over to the left side where I get a positive number of x squareds. Everybody agree? Okay. So how many x squareds am I going to get? 16. Okay, and I've got a negative 60x, and if I subtract 4, I get 36. That's all equal to 0, right? Okay, so if I'm trying to solve this equation, what do I do next? Yeah, good. I could factor out a 4, couldn't I? Right? If I factor out a 4, what's left behind? 4x squared minus
15x
plus. Okay. Okay, I wrote that lightly because that's a step you don't even have to do, right? The next step would just be to divide each side by 4, wouldn't it? Because remember, it's okay to divide both sides of an equation by a number. That's always fair game. But I just can't divide both sides of an equation by a variable. Okay, and there's a reason for that. We'll talk more about that soon, when it's in the context of what we're doing. But for now, just take my word for it. You can't divide both sides by a variable. Like I couldn't divide both sides by x, for example, to make things easier. Okay. Actually, I'll show you why. Instead of just telling you, I can show you. There's a way I can do this. So what if we did, okay, and all I'm doing, I'm just defending that statement that I can't divide both sides by x. So what if I had, I gotta think of a good one here. What if I had something like 2x squared, I'm solving this equation, 2x squared minus 8x equals 0. We'll come back to the last one in a moment. This is an easy one. What am I going to factor out? 2x. Leaving me with, what, x minus 4? Right? Okay, so now what happens if I divide each side here by 2? The 2's cancel, right? Those are common factors. You see why I can cancel those? Because you can only, like I couldn't reduce the 2 and the 4, because the 4 is not a factor, but the 2 is. The 2 is a factor because it's being multiplied by stuff on the top, right? So it's free to cancel. So I cancel those out, and that gives me x times x minus 4 equals 0. 0 divided by anything is 0, right? Okay, now what if I tried to do this? What if I tried to divide each side through by x? Well, those are both factors, so logically I should be able to cancel those, right? Over here then I'm going to end up with x minus 4 equals 0 divided by x, I guess we'd say is 0, right? So what's my solution? Okay, but so what's my solution then? So that would be true when x equals 4. Hey, we got it. What's the problem? I lost a solution. When I divided by x, I lost a solution. What should have happened right here is I should have applied the 0 product property instead and said each of these factors equal to 0, right? And I would have gotten two solutions. I would have gotten the solution x equals 0, which is just a number, or x equals 4. So you see the problem. If you divide both sides of an equation by a variable, you lose a solution, and that's bad, right? But I can always divide each side freely by a number. That's okay. So here, this next step would be, I would just divide each side by 4, right? But why didn't I do that right away? Why couldn't I have just set up here instead? I can see that 4 goes into both sides, so I could have just done that if I wanted to and skipped that step. I get to the same place, don't I? If I just divide each side by the number 4, I end up with the result 4x squared minus 15x plus 9 equals 0. See my point? Okay, now that's a little bit smaller equation to deal with, right? But I still am stuck there. You know, that's a little tougher one, right? Because now a is not equal to 1. Okay? So let's see if we can go further with this by factoring. So what's my next step? Okay, so I gotta find magic numbers again, just like before. The magic numbers have to multiply to a times c. Well, a times c is 4 times 9 is 36, right? So they're going to multiply to that. And they have to add to b, which is negative 15. So that's going to be the sum of the magic numbers. I got to find those two. So what numbers multiply to positive 36 and add to negative 15? Negative 12 and negative 3 are my numbers, aren't they? Okay, so let's do this. You guys all know how to use bottoms up. That's the way you learn how to do it. But let's see if you can remember how to do it with my new tricky way that's algebraically rigorous. So we can factor by grouping. How's that work? What am I going to do? Okay, so I'm going to take the middle term and I'm going to split it into 2 using my magic numbers, right? So we've got 4x squared. And does it matter the order? No, doesn't make any difference. You might think it should, but it doesn't. You're going to be able to factor by grouping either way and you'll get the same answer. If we had a little more time, I'd prove it to you, but just believe me for now. Okay? So We split that down the middle. Right, now what? Okay, I'm gonna factor out the greatest common factor of group 1. So what is the greatest common factor? 4x. Okay, so I'll take out a 4x, leaving me with, okay, good. And so then I'm gonna have a plus sign that's separating the two groups. Now, what do you know about the second group? Okay, it has to have that same leftover, it has to, or grouping won't work, but it will. If you can find magic numbers, factoring by grouping is guaranteed to work for a trinomial. Every time. If you can find the magic numbers, it always will work. So what's going to be the greatest common factor I have to undistribute to get that?
-3.
Okay, and now you have it, don't you? Right, now you've essentially got everything factored. If I've got group 1 and group 2, if I undistribute the x minus 3, what's left behind? From the first group, I get a 4x. From the second group, I get a -3. And so if we just write that a little more simply, isn't that just x minus 3 times 4x minus 3? Okay, and those are both, remember, that's all equal to 0, right? And so then all I would do is apply the zero product property, and we're done. Okay? You got it.